In this video, we're going to see the method of Lagrange multipliers for one constraint, and then we're going to apply that method in example 4.3.1. When f of xy has extrema subject to the constraint g of xy equals k, and when the gradient of g is not equal to 0, the extrema may be found by first solving a system of equations, and that system of equations is given by the gradient of f at xy, and the constraint curve, g of xy is equal to k. And it's worth pointing out that this is a vector equation, so actually that's two equations in one. So really, this system of equations is a system of three equations, three unknowns. F sub x at xy has to be lambda times g sub x at xy. Same thing for f sub y. So our unknowns are lambda, x, and y. And finally, g of xy is equal to k. The solutions out of this system of equations will give us points where we can evaluate f. If we evaluate f at all points from step 1, we'll find, remember that this is assuming that f has extrema. If f has a minimum, then the smallest value, the smallest function value from step 1 will be the minimum. And if f has a maximum, then the largest, the maximum. Not have extrema. This system of equations might still have a solution, and that solution can fool us into thinking that it's a maximum or a minimum. Don't be fooled. Second, this method generalizes well to functions of more variables, so we can do the same thing when f is a function of 3 variables or more. Example 4.3.1. We're going to use the method of Lagrange multipliers to maximize the area of a rectangle inscribed above the x-axis and below the parabola y is equal to 9. Then we'll verify that we have the right answer using methods from Calculus 1. So let's draw the situation, and we'll come back and take a look at the method. So we have a parabola, which is the parabola y is equal to 9 minus x squared. Notice before we do anything else that that can be rewritten as x squared plus of xy equal to x squared plus y, and that this is the curve g of xy is equal to 9, a level curve where the k value is 9. Now we are looking to inscribe a rectangle below the parabola and above the x-axis. So here's the rectangle whose area, we take this point x, y, then the length of the rectangle is x, the height is y, and so the area is 2x times y. So what we really want to do is maximize the function a of xy, which is x times y, subject to the constraint g of xy. So let's do that by following the method that we just saw above. We're going to create a system of equations by setting the two gradients equal and using our constraint curve. So let's calculate the two gradients. Oh, a little mistake in my area. 2xy. So the gradient of a at any point xy is going to be, so if we take the derivative with respect to x, we'll get 2y. Derivative with respect to y will give us 2x. The gradient of g at any point xy is 2x and 1. And so our system of equations becomes 2y is lambda times 2x. 2x is lambda times 1. The x component must be lambda times the x component, and the y component must be lambda times the y component, with the constraint that x squared plus y is equal to 9. Now this is what we need to solve. So if we take a look here, we can divide this, not by lambda, by 2. And we have that y is equal to lambda times x. Here from this equation we have that lambda is 2x. So if we put those together, y is equal to 2x squared. We'll take that and substitute into the last equation, so that x squared plus y becomes x squared plus 2x squared is equal to 9, or 3x squared is equal to 9. X squared is 3, and x is plus or minus root 3. Now obviously we want x to be a length. Root 3 would be over on this side, but if we want x to be a length, we'll take it as greater than 0. Therefore, x will be root 3. If x is root 3, y is 2 times x squared, so 2 times root 3 squared, y is going to be 6. And the area that we're looking for, area is 2xy, so 2 times root 3 times 6, or 12 root 3. Now, we really should prove that this is a maximum value, but if we take a look geometrically here, the x has to go on this side of the parabola, and so obviously rectangles drawn down here will be smaller. Rectangles drawn up here will also be smaller, and so there has to be some maximum value in between the two, so we can say that geometrically this is a maximum area. So there's the method of Lagrange multipliers. Now what would you have done in Calculus 1? In Calculus 1 you would have done the same beginning. You would have said that a is 2xy, but you would have substituted. You would have said y is 9 minus x squared, and you would have put those two things together, and you would have created a function a of x. A of x, which is 2x times 9 minus x squared, or 18x minus 2x cubed. You would have then taken the derivative a prime and gotten 18 minus 6x squared, and you would have looked at places where a prime does not exist, and there are none, and places where a prime is equal to 0, which means that 18 minus 6x squared would be equal to 0, x squared would be equal to 3, x is equal to plus or minus root 3, and you would have continued by finding the y, finding the area, and proving that the area was a maximum. So the method of Lagrange multipliers here gives us an alternate method for functions of two variables where we might have been able to make a substitution and use this, solve this using Calculus 1 methods. But we'll see in the next example that it lets us have access to maximization problems of functions with more variables.